Hello, ladies and gentlemen, and welcome to this session, Green Hydrogen, What's Next? I'm Giles Dixon, I'm the CEO of Wind Europe, and I'm delighted to be joined this morning by Miguel Serra and Magnus Killingland of DNVGL, and by Kasper Tekkelsen of Green Hydrogen Systems. Miguel, tell us, wind energy to clean hydrogen, how does it actually work? How do you convert wind energy into hydrogen?
Thank you very much, Giles, for the introduction and your question. Before I answer that question directly, I would just like to give a bit of context and background to hydrogen. I would like to start by saying that already there is a large market for hydrogen, okay? But all this hydrogen, or most of this hydrogen, is coming from fossil fuels, mainly from natural gas and from coal. Okay, and of course, this means that these processes are responsible for emissions of CO2. To produce 1 ton of hydrogen from fossil fuels, you produce about 10 tons of CO2. Okay, and this means that today in the world, about 800 million tons of CO2, okay, are coming from hydrogen production. And to give an idea of what this means, this is the equivalent to the emissions of a country like Germany. Okay, so there's already a huge potential, to reduce emissions just by greening this hydrogen. So alternatively to fossil fuels, we can produce hydrogen using renewable electricity. By splitting the water molecule into hydrogen and oxygen in devices called electrolyzers, which are electrochemical cells connected to make stacks, and these form the heart of an electrolyzer. And with renewable electricity, that's how we can produce green and clean hydrogen.
Got it. Okay. And the hydrogen that is being consumed today, who is consuming it?
Right. So the hydrogen that is produced today, which is about 70 million tons, more than that today probably, is used almost exclusively as a feedstock, okay, for different processes. One very important is in oil refining, okay, because hydrogen is used to remove sulfur. Okay, from oil, okay, and this is important to produce, let's say, clean burning petrol and diesel. Okay, another very large consumer of hydrogen is the production of ammonia, which in turn is used to make fertilizers. Okay, and we can expect the demand for hydrogen will continue to increase. Okay, because both these applications, both producing fertilizers and producing, say, cleaner fuels, we can expect that these will require, let's say, more hydrogen in the coming decades. And there are some, let's say, lower volume applications, which are, for example, in the semiconductor industry or in the metal finishing industry.
Okay, and what other applications might hydrogen have in the future? I've heard people talk about making steel using hydrogen, or having hydrogen fuel cells in trains, having hydrogen buses, and so on.
That's right. So steel is a very very interesting area because steel, let's say, requires coal, okay, or coke to reduce the iron ore. To metallic iron to produce the steel, okay, and steel production is responsible for a lot of CO2 emissions today. So, say, green or low carbon hydrogen could be a way to decarbonize steel production. So that could potentially demand very large quantities of green hydrogen. Okay. So far we have only talked about say, using hydrogen as feedstock, but of course there's also the potential to use hydrogen as an energy carrier okay, as a fuel for transport, either directly as hydrogen or some synthetic fuel derived from hydrogen, which could be ammonia, okay, or methanol or some other type of synthetic fuel. It can also be used as a fuel for to produce heat, okay, either in let's say residential applications, but also industry applications requiring high temperature heat. And it can also be used to store, let's say, renewable energy, and provide some seasonal kind of energy storage. So yes, there is a very large potential for hydrogen in the future.
Okay, thank you, Miguel. So the hydrogen that is consumed today is fossil-based, it is dirty, but the plan is to have more and more clean hydrogen produced from renewables, and you've explained to us how that process actually works. Magnus, tell us, how big a role do you think renewable hydrogen will play in the total hydrogen market? And within that, how big a role will wind play?
Yes, there are many estimates and scenarios for hydro production for the future going forward. And our publication, Energy Transition Outlook, estimates that the hydrogen production will increase from about 70 or 80 million tons today, as Miguel said, and more than double to 190 million tons by 2050. But that could also be, of course, much more with the more ambitious strategies that we see today. And that means about 80 million tons of green hydrogen in real terms, the same as is produced from fossil sources today, and much of that can come from wind. So by 2050, we estimate that blue and green hydrogen could represent almost 6% of global energy demand. And we also see that, for instance, the EU hydrogen strategy states that by 2030, EU should have about 40 gigawatts of electrolyzers. That means about 10 million tons of green hydrogen production per year. And this could mean about 120 gigawatts of new wind and solar, where the majority can come from wind. And I also just read a report from the Fuel Cell and Hydrogen Joint Undertaking, which summarized the EU 28 national plans, where they have two scenarios. And the estimates for the national plans means that they could have between 18 and 70 gigawatts of onshore wind and between 2 and 8 gigawatts of offshore wind by 2030, which could provide up to 50 gigawatts of electrolyzers, meaning 7 to 8 million tons of hydrogen per year in Europe alone. And that means 10% of global hydrogen production of today, which has to replace a lot of this grey fossil fuel-based hydrogen.
Okay, thank you for that, Magnus. So just to be clear, the EU wants 40 gigawatts of clean hydrogen by 2030, correct? Yes?
Yep.
And to deliver that, we need to build 120 gigawatts of wind and solar over and above what we're already planning to build just for electricity generation.
Yep.
That's correct. Okay. That's a lot. Okay, thank you for that. Now, tell us, presumably, some wind farms might be dedicated to hydrogen, producing electricity for electrolysis and for the hydrogen market, and some wind farms may not be playing any role in the hydrogen value chain at all. But I guess for a lot of wind farms, some electricity will go into the grid for consumption as pure electricity, and some will go into electrolysis. I mean, how do you see the market evolving? How far will we have hydrogen exclusive wind farms?
Well, we see that you want to operate the electrolyzer as much as possible with 8,000 full load hours. We have been involved in some pilot projects where you connect the electrolyzer directly to the wind power, and then it has to ramp up and down. So there are many challenges with that. But you have to have, I think, both combination of power from the grid and from the wind to have a very economical case for the electrolyzer. But we see that there are, for instance, in the North Sea, quite a few projects which are exploring hydrogen production directly in the wind turbine or on platforms or energy islands, where we are a part of quite a few, both in Dutch, German, Danish, and Norwegian sea areas. But there's also coordinated efforts to have new grid setups with energy islands, and then also have electrolyzers on those islands and transporting hydrogen with pipelines to the clusters around in Europe.
Okay, thank you for that, Magnus. Now, Casper, Green Hydrogen Systems, your company, you make these electrolyzers, the crucial machines in the middle of this green hydrogen value chain. What's your view, first of all, on where is the best place to locate electrolyzers and to do the electrolysis? Is it next to the wind farm, or do you transmit the electricity through the transmission network from the wind farm to the point where the hydrogen is going to be consumed, and you do the electrolysis close to the point of demand? Which way round is it going to be?
It's going to be both, of course, depending on how the situation is. But right now, it's of course close to the offtake. The hydrogen market is just kicking off, and in order to have a viable business case, it's easier if you don't have to transport your hydrogen too far. However, that said, the price of hydrogen is very dependent on the price of electricity. So you need access to cheap electricity as well. So if you have a wind turbine or solar farm nearby and an offtake of hydrogen, that's of course the ideal situation.
Okay, thank you. Let's talk about costs. You've put your finger right on the key issue. Producing green hydrogen via electrolysis is more expensive today than producing conventional hydrogen. How much more expensive is it, and how quickly are the costs going to come down? Casper, to you first of all.
Well, it is more expensive right now, and how much more is really depending on the setup and where you get your electricity from. So it's hard to get a precise figure, but at least a factor of 2 in some cases, and maybe less. However, the prices are dropping very rapidly now, and especially it's driven, of course, by the large amount of renewable electricity you see coming into play. That you also see, for renewable electricity, you see a very rapid decrease of electricity prices, and that's really the key driver for using green or renewable hydrogen. So when it's going to happen, when we hit fossil parity, that's of course really dependent on your location. So it's not a one answer for the entire world. It depends on where you are, what kind of offtake you have, what kind of grid limitations there are in your area, and it will happen gradually for different business cases. And that's a good thing, because you'll have a market that helps kind of do the transition into lower prices and drive the cost down for electrolysis.
Okay, 2 specific follow-up questions. We've talked about load factors in the electrolyzers already. Can you confirm the significant efficiency and cost advantage in running those electrolyzers at least 50% load? Ideally more. How do you see it?
So, in general, you don't want to pay for overcapacity. That's, I guess, how it is for all kind of equipment you have. So once you make an investment in some type of equipment, you want to utilize it as much as possible. And that makes, of course, sense. But because the price of electricity is such a key factor in the cost of hydrogen, you can, of course, speculate or use only when the electricity price is low, especially if you're grid connected, or if you have an island mode or just a direct coupling to renewables. Then of course you don't have no choice but to produce once the power is there. It is important. The load factor is of course important. The higher load factor you can have, the lower price of hydrogen. However, we will see in the future, of course, low load factors on electrolysis as well, especially in connection with very, very cheap solar power. And that's something that will happen. It's probably not the best case now, but it will be in the future.
Okay, And besides load factor, the actual size of the electrolyzer is also central to getting costs down. Now, I've heard some people say we will have 100 megawatt electrolyzers at some point in the latter half of this decade. Others say, look, today we only have 2 megawatt electrolyzers in use. What's the reality here?
So first of all, yeah, I mean, market volume is the driver for low cost, and not necessarily the size of electrolysis. Of course, for a large electrolysis plant, there will be some benefits for development costs, but you will also have modular systems of electrolyzers you can deploy on a very small scale and still get good prices for hydrogen. So that's one thing. 100 megawatt plants, you'll probably see them in about 4 years' time. And bigger plants will come shortly after. The market is really kicking off now, and these types of projects, of course, have development times in the range of 4 to 5 years, but you'll see a lot of projects in that size range in that time.
Okay, thank you. Miguel, a question for you now, which in fact has come up from the audience. We're talking about dirty fossil, conventional, existing hydrogen, sometimes known as grey hydrogen. We're talking about green hydrogen, produced from wind or solar, but there's also blue hydrogen. Could you tell us what blue hydrogen is, please?
Sure. Yes, blue hydrogen refers to, let's say, the technology, the possibility of capturing the CO2 emissions and storing them underground for long term. And we think that this will also be, a very, important aspect because, of course, there are still many, point sources of CO2, many existing, plants. But of course, they can gradually, let's say, blend in, green hydrogen and make this transition. But they will still be emitting, CO2 for a long time. And if we want to reach, the net zero targets on time and make the transition faster, I think we also need blue hydrogen. And of course, there is a lot of, let's say, potential. The technology is also mature. I'm not an expert in blue hydrogen. Certainly, DNV has experts in blue hydrogen, and I think it's they complement each other, and we need both.
Okay, so blue hydrogen is conventional, dirty, fossil-based hydrogen plus CCS, basically. And by applying CCS, the idea is you make it sort of clean. I think in DNVGL, you produced a study with Eurogas recently, and you identified what you called a 1.5 degree tech scenario. The European Commission also has a 1.5 tech scenario. Interestingly, you seem to have higher numbers for the volume of CCS in the energy mix than the Commission has in its own 1.5 tech scenario, and you had lower numbers for renewables and lower numbers for hydrogen, interestingly. Would you like to comment on that?
Well, I don't know the numbers. I don't have the numbers off the top of my head. What I can say is that our energy transition outlook that we publish, every year. Of course, we consider many factors, and one of them is policy. There's a lot happening in hydrogen, and especially in terms of policy and incentives. And especially after COVID-19. So it could be that because of these differences in the inputs, in the boundary conditions, maybe we have a slightly higher estimate for blue hydrogen. But I don't know if Magnus perhaps can comment more on that.
Yes, in our energy transition outlook, we are considering about 50-50 green and blue towards 2050.
Okay, thank you for clarifying that. Now we have a question which I'm going to put to you, Caspar, about the different types of electrolyzer technology. The question is, has the Alkaline electrolyzer reached its final point in terms of technology improvements? And will the PEM electrolyzer in future be the dominant technology? How do you see it?
So first of all, no, I definitely do not see that the Alkaline has reached the final point of development in no means at all. I think that the development within Alkaline electrolysis has been very, very slow or almost stagnant for many years, and there's a huge potential to improve it even further. And people have a tendency of, picking what do you see as the winning technology. I mean, it's not about technology, it's about the price of hydrogen. Whoever can produce the cheapest hydrogen in a given use case or in a given with some given boundary conditions is of course the choice of the developer.
Okay, and what about putting an electrolyzer inside a single wind turbine?
Yes.
You like that, yes?
I mean, you could put it inside. You've seen pictures of people putting it on the transition piece. You've seen pictures of people putting it close by on floating platforms, or you can put it on an energy island. There's a lot of different ways of doing this. And the most favorable one is there's not just one solution that fits all. That's basically the point I want to make. You will see in the future a combination of all these solutions.
Okay, Magnus, Miguel, any thoughts from you on that question?
Yes, I can mention that we are part of a very interesting innovation project, Deep Purple, which has integrated electrolyzers in floating wind turbines.
Yes, we had a question also on floating wind and green hydrogen and how well suited floating wind would be, perhaps compared to bottom fixed offshore wind for the production of green hydrogen. Any comments from you, Magnus or Miguel, on that?
I guess you, Miguel, can.
So I'm not an expert on wind and comparing floating and let's say fixed, but yeah, I can say or let's say that the weight of the electrolyzer is important, and that will affect. If it has to be borne, say by the fixed structure, or it will be floating, and how that maybe might stabilize the floating structure. No, so there could be also benefits in that. But as I say, I'm not an expert in the actual integration with the turbine.
Okay, thank you for that, Miguel. Now we're going to bring the costs of electrolysis down. We may also wish to encourage governments to bring in incentives to drive the market and to drive the scale up of green hydrogen production, especially in the next few years. What do you think on this incentives question? Will the CO2 market play a role? Might tax incentives play a role? The German government is talking about climate contracts for difference to drive the clean hydrogen market. What do you think? Miguel first.
For sure. I think that it's very, very important how we tax, the hydrogen, just as it is with, how we tax fuels today. Of course, it's a large source of income for governments today, but it's also another way, to accelerate really the transition to cleaner fuels. Now, so for sure, I think that will be not just the actual fuel, but also the CO2 emissions. So it's definitely a tool that we should use. Yeah.
Okay, thank you. Now we're talking about hydrogen and the role that it can play in decarbonizing those parts of the energy system which we cannot decarbonize via direct electrification using renewable electricity. It's perhaps worth reminding ourselves that the direct electrification of those parts of heating, transport, and industry that can be electrified is always going to be more energy efficient and therefore more cost effective than trying to decarbonize them via renewable hydrogen. At Wind Europe, we think we can electrify 62% of total energy consumption in Europe by 2050. That still leaves 38%, which we cannot electrify: heavy duty transport, heavy industry, and so on. Now, how much of a role will clean hydrogen play in decarbonizing that other 38%? How far can it go? Magnus.
Well, I think hydrogen is a very important part of that for a deep decarbonization, either as compressed hydrogen or ammonia in the maritime industry, and also replacing a lot of gray hydrogen.
Okay, Miguel, would you put a number on it, or Casper?
So, well, I can say from let's say our energy transition outlook that it's let's say for say 2050 we see the split between let's say green and fossil primary energy about 50-50. Of course, it will depend on the region, of the world, but yeah, I totally agree. That just in terms of energy efficiency and resource efficiency, everything that can be electrified directly should be electrified directly. But of course, as you said, there are many sectors, applications where this is just not feasible at the moment. Technologies advance. I mean, other technologies advance, like let's say battery technologies. But we have to make this journey. It's not clear. I think nobody has the answer to that today.
Yes. Okay, Casper, how do you see it?
Well, I mean, it's of course a difficult question. First of all, 62% is also a higher number for electrification. You hear others lower numbers from other players, but in general, of course, it'll play a major role. I can't say if it's going to be 50% or it's going to be more or less than that. That's really depending on how fast the developments happen within hydrogen as well.
Casper, I'm going to put you on the spot on costs.
Yeah.
Now, you say that today renewable hydrogen is twice as expensive as conventional grey hydrogen. When will it cost the same amount? Will it be in 2030? Will it be earlier? I think the metric is euros per kilogram of hydrogen produced, yes? For what they call the LCOH as opposed to the LCOE, yeah?
Yes, that's correct. And again, it's the story is going to happen that you will have some cases where green hydrogen will be cheaper than grey hydrogen earlier, because if you need to build a steam reformer somewhere, it needs to be transported somewhere else in order to utilize. That also adds a cost to your hydrogen, of course. So in some cases, locally produced green hydrogen will be cheaper than centralized production or large-scale centralized production of grey hydrogen. And you'll see that tipping point. It'll move. So in some cases, you'll see you have some business cases already flying with green hydrogen, and they will increase as the price of electrolyzers and the efficiency of electrolyzers improve over the years.
Okay, thank you for that. Now, none of you have talked yet about the role that hydrogen can play in storage, especially longer-term seasonal storage. Nor have any of you mentioned the role hydrogen could play in actually powering gas turbines. People talk about hydrogen to power. You take this pure hydrogen and you put it in a conventional gas turbine. Any thoughts on those points, re-electrification and storage?
Yes, then we see now that the industry is picking the low-hanging fruits with blending hydrogen into existing pipelines and blending 2 to 9% in many places and even more. And there are some pilot projects also rebuilding or actually retrofitting natural gas pipelines into hydrogen. And those are usually also connected to salt caverns where you can store hydrogen in longer-term seasonal. But of course, the cost for storing hydrogen is very high. So you want to utilize existing infrastructure as much as possible. Maybe you, Miguel, has some more on the storage.
Yes, what I can say is this is my opinion. I think this let's say this is like the last mile, let's say of reaching 100% renewable system. No, I think I say renewable electricity is even so it's still a scarce resource. I think we need to use this let's say wisely. And I think until we have systems where we have very high penetrations of renewable electricity, I think just because of let's say, alternative technologies to provide flexibility to the power system and other storage technologies. I think just due to the high costs and the low efficiency of a re-electrification cycle, there can be some niche, let's say, applications where this is already cost efficient, but I think wide scale adoption of re-electrification will still take some time.
Okay, well, listen, thank you very much for that discussion, Miguel, Magnus, and Casper. Miguel, I'm going to hand over to you now to moderate the next 30 minutes, the Meet the Experts part of this discussion. Thank you very much.
Thank you very much, Giles, and thank you very much, Casper, both for moderating and speaking and participating in this green hydrogen session. Thank you very much. Okay, so now I'm going to ask my colleagues at DNV, Ton van Wingerden and Jochem Doma, as experts and on hydrogen, to please join Magnus and myself for this Meet the Experts session. We will be, so I invite the audience who wants to find out more about green hydrogen, the challenges ahead, applications, and so on, to stay. And you can ask your questions. I will be addressing the questions to each of my colleagues. And hopefully we can advance on this very exciting topic. So I'm going to bring up the questions. In the meantime, I'm going to ask both Ton and Jochem if they can just briefly introduce themselves, where they are based, and their experience with hydrogen. Please.
Yeah, well, my name is Ton van Wingerden. I'm based in the Netherlands, in Groningen, in one of the DNV GL offices. I've been in hydrogen for decades right now, producing hydrogen in my first job, and then going into researching new catalysts for steam reformers and using that as input for fuel cells. And lately I've been trying to get hydrogen into the natural gas grids. Some 20 years ago, there was an initiative in the Netherlands. And so we're trying to get hydrogen for heating houses. And now I do feasibility studies. I look into electrolyzers. And I'm also convener of the working group 3 on safety in Sentinel. So,
So I'm Jochem Doma. I'm from DNVGL, working in a Groningen office. That's from the northern part of the Netherlands. I'm mainly focusing on the techno-economic aspects of the hydrogen value chain. So just to give some examples, that is hydrogen production from offshore wind. One of the latest projects was the Nord H2 project that was conducted for Shell and is still ongoing. Another example would be the electrolysis as a solution to grid congestion in areas where offshore or onshore wind and solar basically overloads the electricity system, and there hydrogen could play a role. As a last example, the transport of hydrogen over the world, basically by producing hydrogen somewhere in an area with cheap electricity and transporting it to areas where the hydrogen is needed, either as liquid hydrogen or as one of the hydrogen carriers.
Thanks very much, Ton and Jochem, for your introductions. So I'm going to read some of the questions that we still have here in the Q&A from the audience. And the first question is, what about producing green hydrogen from seawater? I think this is very relevant for offshore wind farms. I don't know if one of you would like to, Jochem, I noticed you started speaking. You want to take this question?
Yeah. Well, of course, for producing hydrogen in an electrolyzer, we need really very clean water with high requirements. So for the production from seawater, it is possible, but of course you need additional treatment steps. So for well, for most of the projects that we've done, we've included a reverse osmosis, multiple steps, and at the last stage, deionizer, to go to the required quality. So it's not impossible, but it just adds some more complications.
Right. Sure. I can add to that it's not just for offshore wind, because there are some areas where, especially in Chile, for example, or in South America, in Australia, where water is a scarce resource. So even it's of course it's also relevant, and there are projects to use seawater to produce hydrogen also onshore. Okay, so there's another question. It says, how does one deal with leakage issues after hydrogen is injected into pipelines and arrives into households? I think, Ton, you can probably say quite a lot about this, given your experience with blending and also domestic, let's say, residential applications for hydrogen.
Yes, first of all, the leakage for hydrogen is the leaks we see is probably similar than compared to natural gas, but because of the physics, the outflow will be around 3 times as high, and then reaching the high concentrations quicker. But you have to take into account the ventilation when it is done inside, and because of the density difference between hydrogen and natural gas, you will see that the dispersion of hydrogen will go faster. Still, you will see, and we've done experiments in houses in the DNVGL laboratory in Spade Adam, where we built specifically houses to see how hydrogen behaves there. So you see that the concentrations will be up to around 10%, which is above the explosion limits of hydrogen. So that needs to be addressed and taken care of. What we see today is that leakage is treated in the same way as for natural gas, but as additional to this, there are now developments to put in sensors on this to make sure that you can detect hydrogen earlier than when it reaches the say 10 or 20% of the lower explosion limit.
Yes, thank you, Ton. Yeah, I think we have some. There's a lot going on, as you say, in Spade Adam in the UK, in the United Kingdom. There was some, there's a lot happening there, and I think there's also public information that they can download from our website about the experiments that are taking place there. Okay, let me see. So here, maybe a question for you, Magnus, because I think you've been recently involved in these type of projects. It says, what role do you envisage for existing but aging North Sea oil and gas infrastructure to support a growing hydrogen industry?
Yes, we are looking into some business cases where we can utilize the natural gas grid there towards Europe, blending hydrogen from offshore wind, which could be attractive cases. But there's also, of course, electrification of oil and gas installations, where you can also provide some power from both bottom fixed and floating offshore wind. So if you want to look at low-hanging fruits, it's the blending green hydrogen into gray hydrogen value chains as the first step. Okay,
maybe now that we're talking about blending, we can say something about say the limits to blending, or let's say what are the challenges in blending. I don't know, maybe Ton, if you can summarize say briefly, how does blending affect natural gas infrastructure?
Not really. If you look at the materials, then they should be fit for hydrogen. If you blend hydrogen into natural gas, there are three levels that you need to take into account. First is the appliances, because it depends on the burners what amount of hydrogen they can take. So you could, of course, it depends on how that looks like, what needs to be done. But of course, if you do an inventory and you see which appliances can deal with, say, 10 or 20% hydrogen, then you can skip that. The second one is the possibilities of flames and explosions when leakage, which I addressed before. That is seen to be around 30%, and then for the high pressure networks, talking about 80 bars or up, there is the possibility of that hydrogen will increase embrittlement in the pipelines, and that is for those high pressure pipelines around 50% to be on the safe side. Now we looked into pipelines for the Netherlands, because Gasunie, the transmission company in the Netherlands, has already determined which pipelines need to be converted for the hydrogen backbone. And we looked into that, and we have calculated that if we keep the pressure there lower than this 60, 70 or 80 bar, but around 50 bar, then the pipeline should be fit. And do you want me to talk about all the materials in the distribution network as well, Miguel?
I think if you can do it very briefly, I think it will be interesting, yes.
Well, in the distribution network, there's a bit of steel and some old materials still from the town gas network. Town gas was 60% hydrogen anyway, and there are plastics. Plastics are new, of course, and these are capable of taking this hydrogen. You may want to have a closer look at the materials used in regulating stations. There have been experiments in Denmark where they see that you really need to look at that in more detail to see what leakage there is, but that's for high hydrogen purposes. And then all the fittings are okay for this, but then of course you need to change for the higher amounts your gas meters, because the volume will increase. And as said, you need to look at your appliances.
Thanks very much, Ton, for this for the detailed answer. Okay. Let me see.
We have one question on which is the longest distance for the hydrogen to be economically produced offshore and then transported. And we have done some analysis on that. And we see that you have to have a certain scale and a certain distance before pipelines become cost competitive. For instance, more than 100 and 150 kilometers, and also more than a gigawatt of electrolyzer. You, Ton, and Joachim have also been looking at that.
Yes, that's correct. You need to look at the pressure for that, and if you have electrolyzers working at 30 bar, then that's then you're technically limited to around 150 kilometers. But the new electrolyzers aim for high pressures that might help. But of course you could also add compressors there as well, and then the distances can be up to 1,000 kilometers already at sufficient pressure. So ocean space is really an option for offshore hydrogen, and pipelines would be fit for transporting that hydrogen.
Yes. Isn't it correct that if you go above those 1,000 or maybe 1,500 kilometers and more than, let's say, about 2 gigawatt, you should liquefy it with ships?
Well, that is an option, but liquefying is not very efficient either, because there is a phase transition from in the hydrogen from I think auto to para, or the other way around. Jochem, you may know that, and that costs about 30 to 40% of energy as well. So that is something you have to take into account. But if you go to liquefied hydrogen, then of course the distance is not a limitation. You can ship it to from Europe to Japan, to the United States and elsewhere. But of course, other options for this type of transport, like ammonia, which is already being shipped in tankers around the world, or with liquid organic hydrogen carriers, which are being developed at the moment as well, would also be an option to use. So you convert the hydrogen to another chemical and then transport it elsewhere, and then decompose it again when you need the hydrogen.
Yes.
Sorry,
So
Magnus,
the-
just yeah.
Yeah, so the project we see now that has bottom fixed or close to shore wind, they usually have electrolyzers on shore. So they transport the electrons to the shore and then make molecules and send that further on.
Yes, and to add to this, Magnus, the pre-session, Giles said we have we produce electricity from wind farms at the moment, and we will produce hydrogen in the future. But I think in between we'll have hybrid wind farms, where you can choose based on what the market asks for or is available, both electricity and hydrogen.
Yes, we have some projects now where we optimize that, looking at business cases, seeing the optimal size of a hydrogen electrolyzer from a certain wind farm.
I have there's a question here. I think it's something we haven't talked about, and I think Don, maybe you probably can say something about this. It's about say standards. Let me find the question. Just one second, please. I lost it. Well, here it is. It says, what is the current state of hydrogen-specific design codes, and how well are these codes suited for repurposing existing infrastructure? But I think we can talk about, generally about codes, and because I think that's and regulations and safety. I think that's an important topic.
I think this question relates back to the answer Magnus earlier gave on repurposing the existing infrastructure, and the pipelines, of course, are designed according to codes for natural gas. If you look at codes that are fit for hydrogen, I think that the ASME codes are the ones that are fit for this. That basically means that you have to look at larger wall thicknesses, so they add something like 20 to 30% to it, based on the pressure. So what you need to do to follow the rules is to lower the pressure, and that's exactly what we've come up with for the Dutch hydrogen backbone. And if you look at all the codes in the hydrogen world, then there is an awful lot of them available to look at the equipment, to look at circumstances, to look at safety. And what you see is that the standardization world is at this moment making an inventory of how existing codes for natural gas have to be adapted to hydrogen, which areas are missing, and what new pre-normative research has to be done. And I see that both in Sentinelic, where I'm taking part of, and in the world, these inventories are being done and are prioritized based on existing literature, on research that's ongoing, and to fit that into the right ways. What you see, for instance, is that for filling stations, that is well developed. They understand very well what needs to be done. For pipelines, they are already there. For electrolyzers, single ones, there is sufficient codes as well. But of course, we need to look at the large scale ones to get it into also that into easy to understand of everybody, the same way of addressing those.
Thanks. Sorry, Magnus, please go ahead.
There are some pilots going on now where you are testing this in Germany and Netherlands, but also Gassco in Norway, which has the responsibility for the pipelines. We also have a project with them with some pipeline engineers here, checking how these new regulations can be improved to more hydrogen blending.
Maybe I would add to that note that it's not so well known because it belongs, let's say, to the say industrial plants, but that already there are, and there have been for many years, let's say pure hydrogen pipelines, operating and operating safely, and there's a huge body of knowledge of handling hydrogen, of course, within industry, but it's not that this is something new, of course. No? Okay, there's another question here. Maybe I can have a go at this one. Talking about, let's say, battery storage. It says, can you talk about the use of hydrogen as storage in lieu of, say, battery storage? As the battery storage technology is well established, is hydrogen storage going to be cost competitive? And I can have a first go at that one, and I can say that, let's say that the current say state of the art of lithium-ion say batteries is definitely, say, very well suited for say short duration storage. We are seeing the costs of lithium-ion batteries coming down as a result of their use in electric vehicles, and there are already very large projects say under construction, even surpassing 1 gigawatt hour of energy storage in batteries. But this is say at the moment economically let's say limited to a few hours of discharge. No, it's let's say they're well suited for, let's say, daily, for example, time shifting of solar PV energy. But when you need, let's say, longer duration times, at the moment there is no clear, let's say, storage technology available. Of course, there's hydropower available that can also store several gigawatt hours of energy. And store energy for, or say, discharge periods of say, in the range of days. But yeah, for this you need, of course, suitable places available for hydropower. So yeah, I think for this kind of longer duration energy storage, hydrogen, and definitely, let's say, seasonal energy storage, hydrogen will eventually play a role. I don't know if some of my colleagues want to add something to this about the role of hydrogen as energy storage.
Well, yes, you're right, Miguel. For a short time, a few hours, batteries are more feasible than hydrogen. But for long term, and we do several projects where we try to use solar power from the sun in the daytime, also at night. So you talk about a 24-hour cycle. There, hydrogen is the preferred option. And of course, if you look at industry, which wants a even supply of energy, then you talk about yearly seasonal storage, then hydrogen is superior, because then you talk about salt caverns, which add only something like 5, 10, maybe 15 cents per kilogram to the price of hydrogen, and that is very, very low compared to batteries. But batteries are improving, I'm sure.
Yes. Okay, there's another question here, interesting, I think, a topic we haven't talked about. It's curtailment, okay? It says, do you have any visibility to offshore wind curtailments, excluding extreme weather, okay? But how this might contribute to cheap green hydrogen at the moment? Could it actually be cheaper now that people want to admit? Yeah, just I think, say the role of curtailments. I think that's a very interesting subject.
I think it depends on how you would see the curtailment. Either if it would be curtailment that happens because onshore demand is doesn't fit the needs, or if onshore demand or infrastructure can't transport the electricity, then there is a need to curtail offshore. The other aspect could be that if there is basically an optimization, looking into the hydrogen capacity or the electrolyzer capacity versus the wind capacity, and there is of course an optimization where you would accept to have a bit of curtailment from the wind farm, but at the same time increase your operating hours of the electrolyzer, because it operates more towards the base load. At the moment, or at least from the projects that we've done until now, there was not yet such an optimization. So there still the wind farm and the electrolyzer would have the same capacity. But at some point, if the wind farm would be floating or in an area where it's really expensive, or especially where the electrolyzer would be very expensive, then curtailment a bit of curtailment might be more, might have a better opportunity. But looking at the current developments where electrolyzers become cheaper, it might even be a good idea to have a bit of additional capacity to the electrolyzer to accommodate for either higher efficiencies due to a lower load, or where you already take into account the degradation of cells and possibly some downtime.
Thanks very much, Jochum. I think we have time for one final question. This is again a new topic. I think, Magnus, I will ask you this question. It says, which is cleaner, electrical and its battery electric vehicles, or fuel cell vehicles using green hydrogen?
Yes, we have many different projects now with hydrogen for buses, and we also do a lot of LCA analysis on different value chains, estimating carbon emissions in kilo CO2 per kilo hydrogen. So the question is, which is cleaner, electric vehicles from green hydrogen or fuel cell vehicles? Well, we see that these different vehicles, they are electric and battery electric. They have battery packs in together with the fuel cell. So that question is, maybe we should phrase it a bit differently. So it depends really on the value chain where the power comes from. So you might have as low as 1 kilo CO2 per kilo hydrogen from hydropower, but significantly more if it is from steam reformed hydrogen. For instance, also the EU taxonomy and also certified regimes talk about 4 kilos of CO2 per kilo hydrogen, and down even negative in some projects where you have biogas being reformed. But it really depends on the electricity grid mix.
Okay, thanks very much. Well, we've reached the end of the Meet the Expert session. I don't know, before we say goodbye, if there's maybe some topic that you would like to have make some final remarks, or something that you felt that we didn't touch upon, or you think that is everything more or less clear that we spoke about?
Maybe we can mention a bit on costs, because we are heavily involved in blue hydrogen, that we mentioned a bit earlier. And as we said, there might be a mix of 50-50, but we see that green hydrogen from the cheapest sources might be competitive with blue hydrogen within 5 to 10 years. But the average win to hydrogen and green hydrogen might be more competitive than blue for a while, before blue kind of catches up. So that's the race for the bottom. Might be a bit bumpy, but they will live in symbiosis in the future, both blue and green.
Thank you. Well, thanks very much, Magnus, Ton, Jochum. I would just say that you can contact us at the booth. So we will be happy to answer if you have any further questions. Thank you very much for participating, to the audience, and sending in your questions. Thank you to the speakers, to the experts, for answering the questions and sharing your knowledge, your expertise. And we look forward to working on hydrogen in the future. Hope you enjoy the rest of the conference. Thank you very much.
Bye-bye.
Thank you.
Bye-bye.